Hello everyone. In this session, we will learn how to compute slope and deflection of the beam using conjugate beam method. First, let me read out the problem. Determine the slope at the ends and maximum deflection of the simply supported beam carrying UDL throughout its span using conjugate beam method. This is the simply supported beam loaded with W kilonewton per meter over the span L. We need to follow 4 steps for computing slope and deflection. Let me go through that. Step 1, to draw bending moment diagram. Step 2, to draw M by EI diagram. Step 3 is to draw conjugate beam. Step 4 is to compute slope and deflection. Let me consider the real beam as it is given in the problem. For this, we will write the bending moment diagram. That is step 1. This will be our bending moment diagram. And next, we need to draw M by EI diagram. That is, moment will be there divided by flexural rigidity of the beam, that is EI. Therefore, the step 2 will be this one, M by EI diagram. It is WL square by 8 EI. Now we will move on to step 3. Step 3 is to draw conjugate beam. As per law of transformation, our beam has hinged supports. Therefore, our conjugate beam also will be having hinged supports. So this is our M by EI diagram. So at point A, there is a hinge support, and also at point B, there will be a hinged support. So this is a conjugate beam loaded with M by EI diagram. Next, we will move on to step 4, that is calculation of slope and deflection. As per conjugate beam theorems, slope at A and B will be equal to shear force at A and B. Shear force at A and B can be calculated as follows. It is denoted as VA, and its support it can be written as VA and VB. These are the slopes, theta A and theta B at the supports, and deflection will be at midspan, that is delta C. Since our parabola is symmetrical, both VA and VB will be same. Therefore, VA will be equal to VB. This will be equal to area of parabola divided by 2. Therefore, area of parabola is 2/3 of base into height. Base is L. Height is WL square by 8 EI. Therefore, VA will be equal to VB. This will be equal to WL cube by 24 EI. As per the theorem, slope at A will be equal to shear force at A, and slope at B will be equal to shear force at B. This will be equal to WL cube by 24 EI. Only theta A will be in the clockwise direction and theta B will be in anti-clockwise direction. Next, we will move on to computation of maximum bending moment. As per conjugate beam theorem, maximum deflection will be equal to maximum bending moment at midspan. First, let us consider the M by EI diagram, conjugate beam. Shear force is acting at the support A and shear force is acting at support B. A and B are the two supports. Since the parabola is symmetric, I will consider only half of the portion for computation of bending moment at point C. The load will be acting at the CG, this area load, let me call it as W1, and the distance between the CG point to the point C, let me call it as X1. The distance between A to C is L by 2. So bending moment at point C will be equal to VA into L by 2. Since VA into the distance between AC is creating a clockwise moment, therefore it will be a positive. W1 and X1 is creating anti-clockwise moment at point C. Therefore, I will consider it as a negative. VA, we already know that value, WL cube by 24 EI. Let me calculate W1. W1 is half of the area of the parabola. It is 2/3 of L into height is W L square by 8 EI. It will be WL cube by 24 EI. The distance X1 is 3 by 8 times of L by 2. Therefore, X1 is 3 by 8 times of L by 2. Substituting the values VA, W1 and X1 in this equation 1, we will get L by 2. Now let me take this value WL raised to 4 and 48 EI separately. It will be 1 minus 3 by 8. Further simplification, we will get 5 WL raised to 4 divided by 384 EI. This is the maximum bending moment at C. As per the theorem of conjugate beam, maximum displacement or deflection will be equal to maximum bending moment, that is 5 WL raised to 4 divided by 384 EI. Now let me move on to another problem. Determine the slope at the ends and maximum deflection of the simply supported beam supporting a point load at the midspan using conjugate beam method. This is the beam simply supported loaded with a point load at point C. So first step is to calculate the reaction. The reaction RA and RB will be same because the load is acting at the midspan of the beam. Therefore, bending moment at point C will be equal to PL by 4. So this will be the bending moment diagram. Step 2 is to draw M by EI diagram. Since the bending moment is in the hogging direction, the load will be acting downwards. This is the M by EI diagram. That is, M is PL by 4 divided by flexural rigidity, that is EI. Step 3 is to draw a conjugate beam. Since here both the supports are hinged, in the conjugate beam also hinged supports remains hinged as per the rule of transformation. So this will be our conjugate beam loaded with M by EI diagram. So we will be having reactions VA and VB, that is shear force. Step 4 is to calculate these two shear force. VA and VB will be equal to area of triangle by 2. As per the conjugate beam theorem, slope at A and B will be equal to shear force at A and B. Therefore, shear force at A and B can be calculated as VA is equal to VB is equal to area of triangle by 2. Area of triangle is half into base is L into height is PL by 4 EI divided by 2. On simplification, we will get VA will be equal to VB will be equal to PL square by 16 EI. Therefore, theta A will be equal to theta B will be equal to PL square divided by 16 EI. Now let me move on to computation of bending moment. As per conjugate beam theorems, maximum deflection at midspan is equal to maximum bending moment at midspan. So first let us consider the M by EI diagram, that is PL by 4 EI. Shear force VA and VB are acting at the supports. The distance between supports is L. These are the supports A, B and midspan C. The distance between midspan and one of the support is L by 2. So in order to calculate bending moment, I will consider half of the portion of the triangle since M by EI diagram is symmetrical. So the load of this triangle is considered as W1, which is acting at the point CG, and the distance between CG and the point C is X1. So bending moment at point C is VA into L by 2, which is creating a clockwise moment, and minus W1 into X1, which is creating an anti-clockwise moment. We already know the value of VA. It is W PL square by 16 EI. Let me calculate the value of W1. It is the area of the triangle 1, that is half into base is L by 2, height is PL by 4 EI. So PL square by 16 EI will be my W1, and X1 value will be equal to 1/3 of L by 2. The remaining portion is 2/3 of L by 2. Substituting all these values in this equation 1, we will get bending moment at point C that is PL square by 16 EI into L by 2 minus PL square by 16 EI into 1/3 of L by 2 PL cube by 32 EI minus PL cube by 96 EI. On simplification, we will get PL cube by 48 EI. That is the maximum bending moment at point C. As per the theorem, maximum deflection will be equal to, at point C, will be equal to maximum bending moment at point C. That is PL cube by 48 EI.